Copyright Stanford University, all rights reserved.
Okay, welcome everybody. I'm David. I will be the instructor today. And so we have 30 minutes before the lecture begin. So during those 30 minutes, the plan was that I can help you set up R if you have problems or answer preliminary questions. So, I mean, raise your hand and I will come to you if you have a question too. Otherwise, that's the prerequisite for the class. So I would like you to execute those little commands in R. And either you copy that from the PDF, which was a prerequisite for the R lecture on the Lane Library website, or you just, type them. You have largely enough time for typing them. Oh, hey, how are you? Okay. Okay, why did it shut down? So the Excel package apparently is not available for Mac OS 6. It's just new. I just discovered that right now. So sorry about that, but yeah, I cannot do really anything about it. Who has a question? That's the one question here, and I will walk. Yes. The multi-core just work on Unix, and it's possible to install it on Windows, but it's really complicated. It's yeah. Yeah, you can. I mean, put your hand, I think, and grab a power adapter. Yeah, I recommend that the class is 2 hours, so plug your laptop if you don't have enough battery power. And there is plug all over the place. Yeah. So there was a question here. The multi-core package? Yeah, the multi-core package is pretty tricky to install. It's, yeah. So selection, yeah, you have to choose a thing. So for example, 68, which is Berkeley.
Yeah, but what I was saying is that the XLux.
XLux doesn't exist, it's XLS.
XLX, so if you do it in RStudio, it can be loaded to Macs.
XLS, not available for 15. Okay, so you can always install it, but and search here, XL6. It's not available. It's new. I have it on mine, so I didn't know that. Yeah. Yes.
The multi-core.
Multi-core package is multi-core. What does it say? Yes, it's not working on Windows. It's unfortunately. I will show you that how to work it on an online server, so you can always use it. Sorry, I didn't hear. So for the foreign package, the one which is here, okay. The second one, it's if you have an old version of R, it was not available for this version. It's pretty new. So if you have 10.13, for example, 2.13, R, it will not work for this version. It will work for the newer version. So the last one, yeah. So I built this tutorial based on the last version of R, 2.15, not 2.15.1, in fact. But yeah. All right, so we still have like 15 minutes, before the class begins. And yeah. Yes. No, it's not. That's the handout of the slides. The package listing is on the library website. If you click on the introduction to our lecture, you have a PDF inside, a link to a PDF. This one yet doesn't work. It's not available for 15. You cannot install it. Yeah, no, XLS doesn't work. It's not available for the last version of R.
Oh.
Strange. Yeah, sorry about that. Yes. It's over there at the beginning of on the first table. Ah, yes. for the people sitting in the back, there is still one seat here. And maybe, I mean, you can almost fit 2 persons here, squeezing in. So instead of sitting on and having your laptop on your lap. All right. Okay, so we're about to start. So I was asked by the library to have, so there should be a signing sheet available, I mean, turning around. I don't know where it is right now. But please sign it, sign your name if you're present. And that's important for the library, as it in fact validates that the people came to the class, and it's important, and we can do it again. And we will get the funding again to do the class. Also, I was asked to remind everybody so that this class is in 2 parts. There is one today from 10 to noon, so that's right now. And tomorrow from also 10 to noon. And that will be the second part, which will be a bit more like high level. What can you do with R, or to analyze genomic data, and or to produce HTML report of your result, and also PDF and everything. And go a bit further on what are the graphic capability of R. I would like to emphasize that there is a supporting website, so with all the code we'll see today. So you can direct your browser to this address. It's on GitHub, so it will be displaying, in fact, the code highlighted and everything for today's session. So I would like to precise that it's a hands-on session, so everybody is allowed to type the code, but as we have many people, I mean, randomly, there will be some people for which the code will not work, either because you forgot a comma, or you forgot a quote, or because the package is not installed, or because it doesn't work for some reason. So during the class, I will not do technical support about why it doesn't work on your personal laptop. But at the end, if you want, you can come and see me and ask if you have a really a tricky question and you want absolutely this code to work. You can come and we can try to solve that together after the lecture. I will try to finish in time, depending on the amount of question I will get back from you on the different steps. I want this tutorial to be interactive. I think we can learn from each other. I mean, a question is never, making sense for everybody. So it's just like, I'm sure if you have a question, many people in the class will also have the same question in the back of their mind. So feel free to ask questions, but not too much that we cannot finish the class in time. Bear in mind that we are, I think, 50 people today. So that will be good, I think. We will have a lot of things to see. All right, it's 10. Let's start. So that will be the part 1. So today we'll have an overview of what is R, what can you do with R, the R ecosystem, I call it. Or can you run the program R? And I would like to demystify that the aim of this first part, demystify that you have to type some command line to interact with R, but it's not that complicated. So we'll see data structure in R. So how does R represent, for example, a table, an Excel file that you have on your laptop, or does R can represent that inside the workspace? After that, we'll see how to import data, export data. We'll have an example for importing microarray data from the public domain. Will be, interactive. If you want to run the code, you are free to do it. It's a bit platform specific, so you have some little step in the middle which are relying on some package which are specific to Mac OS X. But you can also run it by hand on Windows, so it's not that big a deal. After that, we'll go a bit further down on how to program in R, so how to write functions, how to write parallel functions, so to use all the processor available on your laptop. I see that there is a bunch of laptops here, and I'm pretty sure that most of them, in fact, right now have what is called a dual-core processor in it, meaning you have 2 virtual processors on your laptop. But most of the time when you do a computation, you can, in fact, you use only one of them. Or to use both of them at the same time, and take advantage of the processing power of your machine will be the topic of efficient R programming. And after, we'll go a bit further on how to write function and using object-oriented programming. It will be a bit more advanced, and at the end, I will give you an assignment for tomorrow. And it's not an assignment where you get grades, so it's don't worry. It's just like if you want to do it, it will be fun, and you can send me your code. And tomorrow morning, during the first 10 minutes, we'll review the code and of the best solution people proposed, and we'll make a comparison of the speed between the different implementations. And with that, let's start. I would like to remind you that there is a handout to take at the beginning. If you don't have it, maybe people can circulate them, and the rest of the pile can you circulate the rest of the time and take one exemplar if you don't have one already. Yes, that would be good. All right. That's the website. Direct your browser to it. So if you want to follow at the same time and look at the code and copy it and paste it into your R session. And let's start with our ecosystem. So why do we do a class on R and we don't do a class on SPSS and SAS or Stata? Is that R is the benefit of it is that it's free. It's freely available, and that's become the most popular statistical programming language in front of the other systems. It has more than 2 million users worldwide, which is quite substantial when you consider that it's a programming language, and not everybody uses that. There is more than 3,200, that's an old number, 3,200 package, and more than 80 new package a week in R, which are committed to the repositories. Meaning that a package is a library of function. For example, it would provide you functionality for importing macroarrays or importing fax analysis data or any type of data you want. The beauty of R is that it's open and people can submit package to R relatively freely and easily, meaning it has been heavily used to release, what is the new method you use to analyze next generation sequencing data, for example. It's free, as I mentioned. There is package for everything, from statistics to geology to finance. There is a huge community working with R in financial data, so people working on markets data. Ecology, graphics, just pure graphics. The library exists in R, and you have, we'll see some example in the lecture tomorrow. And you have multiple R interface. It's also one of the only programming statistical language that was on the New York Times, featured on the New York Times at least 2 times, one in the old version and in the recent one. You can always download R from one of the major operating systems, Linux, Mac OS X, and Windows. You can download it and install it. So I think that was it. And that's what R looks like. So from the terminal, you can always start R from the terminal or from the R application icon that you obtain when you install the application. And it looks like you have a prompt at the end. And the prompt is, in fact, telling you that it's waiting for a command. You can also use RStudio. So that will be, I think that will become more and more easy to use in the future. And RStudio will be, I would recommend you to start with that instead of starting with a regular R application. And because it's more integrated, you have the graphic on the right, you have your workspace, which is always displayed. You have the console where you type your command, and here you have the files and whatever you type you want to save. So it's a nice way to use R. And I say, as a personal point of view, I think maybe you should start with that. There is other way to use R, which are in the cloud. So you all heard about this buzzword. It means that you use R remotely, basically. You run R on another computer from somebody else, or you rent it, in fact. You can run R on Amazon. Amazon EC2. EC2 is a fancy word to say that, in fact, you buy processing power from Amazon, and they give you back a shell command line. So they give you back, in fact, a command line where you can start R and execute your command over there on a big machine instead of running that on your laptop. It's relatively easy. There is, in fact, a an image for people which are a bit more familiar with running cloud machines. So you can use the bioconductor image. You can also use Cloud BioLinux and other things. But more precisely and specific to R, there is the EBI, the European Bioinformatics Institute, engage you to have a look at it. So it's basically they provide you an R interface. You just double-click an icon on the website, and they will start R on their own server and provide you the interface for you. But on the back, it's not that you run that on their own laptop. You run that on a huge cluster over there. And you have access to a huge amount of computing power for free at the EBI. It's, I don't know if it will stay free, but for the moment it's free, and it's pretty robust, and they have all the package pre-installed, so you don't need to have a problem installing package that what we saw this morning. There is several advantages in running R and in the cloud applications. The main one is that you can, in fact, if you are running your entire analysis, you import your macros, you import your data, whatever it could be, patient data or any type of data you want to analyze, you can import that, run that into your virtual machine on the cloud, and at the end, when you're ready to publish your paper, you save this machine and you say, well, all my analysis and all my settings that I used are on this machine. So everybody is free to check out what I did, what was the step I ran, and in fact, it's reproducible research. So it's a push toward, in fact, providing all the steps you perform in your analysis and not having a black box saying, well, we analyze that in Excel, but I cannot tell you what I did because I click on every button there is. So, and I did some mistakes. So the thing is that it's reproducible research. And you can share your data and share your workflow. R101, we will have one slide or two about how to use R because we don't have the same level of expertise across the board here. And so R is basically, if you want, you can do the Zeus command in real time right now, and you can type Zeus command on your R console. R, from a standpoint of the bare ground basic, is a really fancy calculators. It's just, you type 3 plus 3 will give you back 6, okay? But if you want to go further than that, you can store things in memory. And that's what you would do with the assignment sign. So it's inferior to minus 3, but you can also store something into a variable that you call x or y using the equal sign, okay? So both are similar, and you would say you store inside x, you store 3, okay? And inside y, you store the number 3, the integer. And you can store also the integer 6 into y and x using a double assignment. Or to perform operation, you can square your number, you can add them, you can just use, in fact, the variable directly, and it will give you back the result on the command line. Or to store a vector. A vector is a suite of numbers. And the basic command to do that is called the C for combining data. So you can say you want to combine this suite of number 1, 2, 3, 4. You surround that by brackets, and you put a comma between the thing, between the object, and it will store that into X. And when you type X and you type return on your keyboard, you will have what is contained inside the object 1, 2, 3, 4. When you do an operation on X, it will apply the operation to every element of X. That's what we call a vectorized. So R will apply an operation to every element of the object that you have in front of you. For example, here, I am adding 10 to X, but I don't specify that I want to add 10 to every number. I just say I want to add 10 to X, and it will add 10 to every element of X. And you see here, it added 10 to every element of X. So instead of having 1, 2, 3, 4, I have 11, 12, 13, 14 on the screen. If you want to access one of the elements of your vector, you use square brackets. And square brackets are indicative of an index. So you access this element inside your object. And here we want to access the element 4, and we have the number 4 output because that's what is contained inside at the fourth place. At the same time as you have operation like mathematical operation on object, you can also perform logical operation on your vectors. For example, which element in X are superior to 2, and it will return you a Boolean vector in this case, where you have false, false, true, true, meaning the last two numbers are superior to 2 in value. If you want to have the object of it, if you want to have the object inside X, which are superior to 2, you need to use a combination. So you want, it's important to understand the syntax here. We will use the square brackets to indicate the index. And inside the square bracket, we will give this Boolean vector, false, false, true, true. Meaning, false will tell inside X, inside the square bracket will say, the first element is false, you don't need to output it. The second element is false, you don't need to output it. The third element is true, you need to output it. And fourth element is true, and you obtain, in fact, only the number which are above 2 inside X. So that's an index, and that's how you use an index, giving, in fact, a logical operation inside. A few other things. So if you use the column operator, it gives you a suite of numbers, 1, 2, 3. If you put that inside square bracket, you output the first 3 elements of X. 1, 2, 3. Okay. That's another is NA. So it's to know if one of the elements inside your vector is null. So it means it's not defined. Okay. That's why I show you that is that because, most of the time in your data you will have some empty cells or some empty column or some rows which are in fact empties. But when you will import your data, these rows and those cells inside your table will be represented as NA inside R because they are absent. So or to know where they are, you can use isNA, and it will output in fact a Boolean vector saying false, 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 meaning there is no NA inside X. Here you have a cumulative sum of X, and you can make an operation. That's the first step toward a bit higher level functions. So you can apply function directly to a vector and objects, matrix, and everything. Cumulative sum would give you the cumulative sum of X. You can also have the summaries. That's another really handy function to have what is the minimum, the first quartile, the median, the mean, and the third quartile of your data. And in fact, outside of the screen on the right, over there, there is also the maximum, which is outputted. If you come from another and you learn other language in the past, one key difference between R and the other is that R use pass by value and not pass by reference. Here we create, and I will give you an example here, is that we create a vector of 10 numbers. We store 1 to 10, so the suite of number 1 to 10, and you see it's inside. So when you type X alone, it returns you the suite of numbers which is inside. You multiply every number by 2, and it outputs you the value of X, but multiplied by 2. But the thing is that if you type X after to see what's inside X, X was not modified. X is still 1 to 10, and it's not 2 to 20. Meaning the value inside X were not changed by the operation you applied to it. Okay? That's meaning it's passing by value, not reference. So you don't apply an operation to an object, you apply to the value. If you want to, in fact, multiply and store those values, you would have to store those multiplication multiplied by X multiplied by 2 into a new object using the arrow sign, the arrow inverted sign. So inferior to minus. Is it clear for everyone? It's pretty basic. It's just when you apply that, it applies to the value and not to the object itself. To store the result, you have to store that into a new object. You want to use pass by reference paradigm. So this thing, you have to look at. You can have a look at the r.oo package and also the mutat r and proto package, which provides this functionality to have, I mean, a more classic programming language aspect into your inside R. Okay, so that was the greedy detail, but let's go on and have a look at what R can do. So R is a statistical language, meaning it provides basic mathematical functionalities. So if you want to apply a function to an object, and in our case, that's our object is X, and it's the suite of number 1 to 10, okay? To apply a function to it, we use round brackets, I would say. So those round brackets, okay? It's not square bracket. You type the name of the function in front, mean, round bracket, and you put your object inside. In this case, mean just accepts one object, which is usually a vector, and it outputs you the mean of your vector, okay? You can also use the median, the standard deviation, do the sum of x, or in fact, extract the square root of x. And of course, you can obtain summary information, as I mentioned before. Every function is a bit different, and you have associated to every function, you have a help menu to describe what are the arguments that the function will accept within the round brackets. So for example, mean just accept vectors. If you give something a bit more complex, like for example, the table to mean, it will output you the mean of the entire table, which doesn't really make sense in your case. So you have other functions for doing that. And you might want to discover that by looking online, what are the functions to do what you want, for example, extracting the column means. So, as I mentioned, there is a help for everything, and yes? No, you type help start, like that. Help start, no, you don't put anything in it. And it will start this screen, okay? Help start will start this screen, and in this screen you can have, I mean, basic information about R, so the introduction to R, it's not this course. And you can write extension. You can have also, it's a list of the package which are available, and you have a search engine. But within R, if you want to have a description of your function, you type the question mark followed by the name of the function. For example, you want to have a description of the plot function. You type question mark plot, and it will open a web page, or within your R environment, could be RStudio, R application, you will have, in fact, the display of the help. It's really handy. For example, going back to the mean function, you can type question mark mean, and it will describe what mean is doing, what type of argument it takes. The most important thing is that at the end of this page, you always have an example. And that's usually what I use. I read a bit at the beginning what it does, and I go to the example at the bottom to see how to use it. You know, it's what I like. You always have an example associated with a function. Recommended reading is R Inferno. So R Inferno is a funny thing. It's a story based on somebody which is discovering the language, and it's similar to Dante. Inferno, so Dante from, I forgot the name right now, of course, during the class. So it's pretty funny to read. Somebody was lost inside the language and everything, in a dark forest. Anyway, so the power of R, why is it so popular, is because there are packages, and packages provide functionality for users. There are packages for everything, as I mentioned. How to install package is that first you have to find the name of the package you want to install, copy this name, and install it on your laptop, or on your machine, sorry. Packages are available on CRAN, which means, in fact, it's available on the R project website. They're also available on Bioconnector, bioconnector.org, which is a subset of, it's a different branch compared to the main R project, but it's specialized in biomedical informatics package. So you have a lot of functionality to analyze biomedical data, such as doing macro analysis and next generation sequencing analysis, everything, mRNA-seq, ChIP-seq, everything you can imagine. A lot of people develop in R and publish package to do their own analysis, And at the same time, it would be useful for you to use this package. The thing is that Bioconnector is providing a package with a reference vignette, which is in fact a help manual, which is nicely documented and provide details about what does the function inside the package are providing. How to install a package, you already saw that it was in the prerequisite. So you type install package, and between quotes the name of your package, for example, ggplot2 to do plots. And to install Bioconnector package, you have a different paradigm. So you don't use install package, but you use BioC It's kind of install package, but for Bioconnector. And to update, for example, there is different function. I just put that as a nice perk, is that you can update all your package at once and say check the build and ask for fast. Otherwise, it will ask you for every package independently. The same thing for Bioconnector. So let's go into the greedy detail of how R is storing objects. So for example, you have your data in an Excel file, a CSV file, or a database, okay? And you have everything, and you want to have that inside your R workspace. There is 4 types of R objects that we'll see today. There are 5, there is array, but we'll not cover it. They are not really used. As I mentioned, there are vectors. So vectors are, suite of numbers, characters, integers, whatever you want. But it has to be of the same type. It cannot be from numeric and character and integers. It cannot be of a different type. It has to be of the same type. By default, if you put a letter, a number, and together and store that into a vector, the entire vector would be considered as a character. And so here, as an example, I store a suite of a string. So Lincoln, Roosevelt, and Jackson, and I store that inside X. So what does X will contain? It will contain, in fact, those name as a suite. If you want to replace the second element of the vector, you just assign, you say, as an element index 2 between the square bracket, and you replace that with the value you want. Here in this case, I just replace it with a null value, NA. And you output X after, and you see you have Lincoln, and instead of having Roosevelt in the middle, you have NA, Jackson. All right? Here's a little Boolean operation, a bit more complex than what we saw before. You have, look within the square brackets, okay? You have the function we saw before is NA, and you apply that to X using round brackets. What it will output is a Boolean vector, true, true, false, false. Okay, in our case, it will output, in looking at X, it will output true. Is it NA? It will output null, false, true, false. All right? And when you put an exclamation mark in front, it inverts the meaning. It inverts the meaning. So a true will become a false. And false will become a true. And here you output that, and you will obtain Lincoln and Jackson. I recommend if it's a bit fuzzy for you, try it at home. Try it with and without the exclamation mark, and you will understand what it does. Okay? So, as I mentioned, you can have only one type of data inside a vector. The classic one, I will use the mouse and stop using the laser pointer because I cannot point on the other screen. So, for example, this vector of president is a character vector. You can say the class of X, and it outputs, it's a character vector. Here we store a suite of numbers with comma, so 1.2 and 1.5, and the class is numeric. Here, if we store 1 to 4, so round numbers, and you say, what is a class of X? It's an integer vector. Okay, it's not a numeric, it's not a float value. And here, that the last type of mode and of type of vector you can have is that X can be also logical. So if we say store inside X, what are the elements superior to 2? It will output a Boolean vector, true, true, false, false. And the class will be becoming a logical vector. So it's greedy, it's a bit, why do we explain that? It's that when you will start coding and looking into R, you will remember those things, and you will say, oh yeah, maybe I'm applying my function to a vector which is not of the right type. For example, if you give a character vector to the mean function, the mean function will fail because you cannot extract the mean from a character vector. So, and that's why I'm showing you that right now. A bit more useful are matrices. So matrices in R is, or you store in fact a table, but a table of the same type of data. It will be only of one type. It can be similar to vectors. It can be numeric, character, logical, or integers. It cannot be from another type. So you cannot have, for example, letters and numbers and expect to have characters and numeric inside your matrix. Everything will be imported inside as the same type of value. You can build a matrix. It's not really useful. We'll see how to import data later, but you can build also a matrix manually using the matrix function. Here we store inside the matrix function we will store the number 1 to 10 in 2 columns, okay? And it will put 1 to 5 in the first column and 6 to 10 in the second column. You can do the inverse and you can say store 1 to 10 into 2 rows, and it will output that 1, 2, 3, 4, 5, 6 to 10, all right? Not really complicated. We'll see how to use that when you import data. But the main object in R are data frames. That's what you will see the most often with vector. Data frame can be, it's a bit like a fancy matrix. You can have objects of different type. You can have characters, integers, and everything inside the same, keeping their own value. Here we have, for example, a data frame that I call df, and I say inside df store patient ID, that will be the patient ID, or 1, or 2, or 3. The treatment, that would be drug, placebo, and drug, and the age of the patient. What you see is that when you output the object df, you have a table which is described with a name on the column, patient ID, treatment, and age, and you already have your data nicely formatted like that. You can imagine you have additional column, and the column, I mean, could be, for example, the value of the expression of the gene for those people, or the measurement you did, for example, is they in pain or not, or if they receive, I mean, what is the amount of drugs they receive. You can subset your matrix. You can extract subpart of your matrix and do already logical operation. And you can use a subset function, again, with using round brackets. You say, apply the subset function to df, to our data frame, and you say where the treatment is equal to drug. And it will just output you the 2 rows inside your matrix where you have a treatment equal to drug, okay? So you can imagine more complex queries, and we'll see some after. The list is a really versatile object. So in a list, you can store other objects. So you can store vectors, you can store data frame, matrices, and even list inside a list, okay? So it's a kind of a meta object where you can store other objects inside and have a more compact representation of all your information. For example, in here, in my list, I create a list where I store a vector of characters, orange, banana, and apples, and I also store a matrix. And the matrix is just basically the matrix we saw before, 1 to 10 on two rows. And when you output your value, which is contained into my list, you have the first element as a name, it's called fruits, and it has a vector of characters. And the second element is called mat, according to the name you gave here, and you have the matrix inside. So it's a more complex object. And that's all for the 4 types of objects that are in R. You have vectors, matrix, data frame, and list. And basically, you will always play around with that. It's always how to transform and extract a vector from a data frame, or extract a matrix from a data frame, or everything. Yes? The money sign, the dollar sign is the index. So if you want to access, for example, the fruit inside my list, you would type my list $fruits, and it will output the fruits inside my list, a shopping list. And the same thing. So you can also access, in fact, mat using the same $mat. All right? So data import. that's where we will use, in fact, not use, but I will make an example. I will use an example of the Excel file. So as some of you noticed, the XLS package that I asked to install in advance of this lecture is not installing on 2.15.1, and in fact, it's not installing on 2.15.0. It's brand new. It was not there when I prepared the tutorial. It's so the Excel file we set. The Excel package to import Excel file. Real Excel file inside R will reappear certainly online. I'm sorry about that, but there is not much I can do. So right now we'll see how to import data from text file, from SAS, SPSS, Stata, or Excel. We'll also see how to connect to database. And database, I will make an example of connecting to a MySQL database, but basically you can connect to an Oracle, a CouchDB, a MongoDB, or SQLite. It's fancy term to say that it's different type of database, okay? If you don't know what it is, it means you don't need it for the moment. That's it. You can import also Weka file. Weka is a data mining, machine learning software which produces own type of file. It's why I put that in, because it's quite a powerful platform to do data mining. You can also import and export R file that allow you to interact with other partners and say, well, you can import this file directly into your R session. We can also import HTML tables, so we can scrap, in fact, web page and import the table within a web page. Yes? Oh, yeah, so it's totally involved to import. It's basically a text file. It's provided into a next generation sequencing package. We'll see an example tomorrow. So if you want, you can try this example right now as we speak. We'll try to upload a text file into your R session. And here is a little thing. It's not that simple. Is that giving a URL, so the web address where the text file is, and I give that to the function read table on the second line here. So read table take the path inside, where is your text file inside your computer. It can be on the same folder where you run R, but it can be, for example, on your desktop of your laptop. So, but here, instead of giving, for example, desktop mytextfile.txt, I'll give, in fact, a URL directly to it, and it will be able to fetch from the website the text file and read it and store it in R. It's already kind of more advanced. You don't need to store your data locally. You can already have everything on a web server and download it. So here you have between the stanford.edu / you have a tilde mark, okay? So the average mark. So don't forget that, otherwise it will not work. And if you type that, you store that into an object which is a vector, but a vector of one element, a character vector called URL. You say read table, read the URL. The separator between the field would be a comma, because we use a CSV, comma separated value file. And there is a header on the file. So you say header is true. Okay. If you don't say header, it's true, it will import the first row as a data value. Okay. Oops, what did I do? Yes, and after that we use the function head to display the first 6 lines of your data, and you will see it. So if you want the pivot object that which is the result of downloading the file from internet, is called pivot, and it contains a table with the first column is gene, the second column are conditions, and the third column are values. You can imagine that's your PCR experiment, where you tested a bunch of genes on different conditions for your cells. And if you are, because we are in the School of Medicine, I hope it makes sense, this example. And if you want to know what type of object is pivot, is a utype class, and you see it's a data frame, meaning it's a more complex object, and you can have characters vector inside the gene, but you can also have numeric value inside value, in the column value. So that's for importing text file. So I hope it works for you. If it doesn't work, we can have a little session after the talk. So one key package to provide import function is a foreign package. So the package foreign is able to import a lot of type of file, and in fact it's covering the majority of the file I described before, like SAS, SPSS, Weka, and all the type of file which are available inside foreign. To have a description, a complete description of foreign, what type of file foreign is able to import, you type inside R help bracket package equal foreign, and it will give you the help for this package, and you will be able to see all the functions which are inside foreign. Okay, you need to install the package before. You cannot have this help if you don't have the package on your local computer. For example, one of the key functions, which is not available for the majority of you, unfortunately, is read Excel file. I'm sorry about that, but you can obtain the help about read Excel file. It's pretty powerful, and I'm really, I feel bad about that. So read Excel file, you can choose your Excel file, but you can also choose the sheet inside your Excel file. So use all the type of functionality which are stored inside Excel, and you will have access to the multiple subtype of Excel file you can have. You can also use the XML package. So here I show you 3 packages: foreign, XLS, and XML. XML is to read XML file, and you certainly know HTML. HTML, that's what web pages are made from. Okay, it's basically an XML format. So you can read HTML file directly inside R, and you can use this function using read HTML table. And here is an example. We read from the website iris.edu, and we'll read, in fact, a table, which is, if you open this web page, iris.edu sysmon last 30 HTML, you will see basically a web page with a table in it. A table of the earthquake, which happened in the last 30 days. Okay? And you can read directly this table and don't have to, in fact, copy every value by hand and put that into an Excel file and import the Excel file into R. You can directly read the table in HTML on the web page, import that inside an object that you call earthquake, EQ. For more information on how to import different type of file, what are the detail about it, I recommend reading the R data import and export. I cannot go further because we want to cover other subjects today, but it's a lot about, that's the first step. That's the first step before doing your analysis. So that's why I spend quite a lot of time on that today. So if you want, you start the help start, empty brackets, and you will have the help coming up, and you will have a function for everything. Yes? So sorry, can you repeat? Oh, saving, exporting file? Yes, that's the next slide. We will see first how to manipulate data, and after how to export it, and I will show you how to save your data. Yes. So it often happens that you obtain your data from somebody else. There's a core facilities that did the experiment for you. They give you FASTQ files, they give you text file of your gene expression, or they give you file from something. It's in fact the case where you have often to transform your data, remanipulate them before you're ready to perform your analysis on it. One of the key functions to do that is, let's have a look at the type of data that I asked you to import just before. So that's the pivot table. The pivot table has 3 columns, okay? In the first column, you have the genes, and you have the condition and the value. But it's in fact an expression file, okay? It's the expression of gene MPP001 in condition copper, and that's the value for it, okay? But you see that at the bottom, you have also other conditions. So you look at the bottom using the tail function, and you see that the file is in fact having 3 columns, and the genes are repeated. So you have the gene MPP01 is repeated for different conditions, for the condition copper, pizza, Cheetos, chips. And so what you want, in fact, to obtain at the end is that you want a square matrix where you have the condition as column and the gene as rows. But one table, okay, with multiple columns. And how to do that is to use, you don't do it by hand, and so you can use the reshape package. The reshape package, so you load the package, you install it if you don't have it already. And what you do is that, here I just show you the result, you cast the data frame. So the table, you have it, and you say you want to reorganize pivot using gene by condition. So you remember, you have gene and condition and value, that the 3 column, and that the name inside your object. And you want to reorganize, you want to cast it and reformat it as gene by condition, so that the tilde mark in the middle here, sorry, doesn't display well on the PDF. And here, we just display the first 2 rows because otherwise it doesn't fit into the slide, but that's a really handy feature. If you want to reformat the table, and it will put inside in the middle the value that were used. You can also subset, we already saw that, and you can say inside pivot, subset the value which are where Cheetos is superior to 0.02, and you obtain only the rows inside your table which are fulfilling the condition you put inside subset. As a nice thing, to do tonight is to repeat those experiments, to load those files and try to copy and paste those, or type it again and copy and paste those commands and to see what it does and why what are the parameters you can play around and everything. Okay, it's you have a kind of a learning curve to R, of course. It's not so easy. It's still kind of a programming language that you have to learn a bit. So a bit more on subsetting your data, and I would like to ask to you which one of you are familiar with SQL? So the language SQL. Raise your hand. 1. Okay. So SQL is a language used for database. It's what is called a third generation language, meaning it's a language made to query your database. You don't do really fancy programming in SQL. You basically you select data from your tables, which are inside your database, and you extract only the data you want. In our case, we can use SQL within R, and you can apply that to your data frame. Meaning, you remember the example of the pivot table we just transformed, when we have the gene on the rows, and on the column we have the condition, and we have the expression values inside. We just want, for example, to select all the rows and all the columns from pivot where the Cheetos, so the column Cheetos, has a value of 0.02, superior to 0.02, and it will output it for you. That's SQL, and if you are familiar with SQL, you see the power of applying that not to a database, but to R object directly. So you don't need even to build a database. The system will build a database for you on your table. And you can use the SQL language to query your table. So that's pretty, you can do really complex operation and add, for example, you want the people that, for example, you have a table of patients and you want the people which are above 30 and which are male and which receives a drug treatment. And you can accumulate that. So you would say where the patient is male and age is superior to 30 and treatment is equal to drug. So you can accumulate that. It's really easy as a language. So you can, really learn that pretty fast. I think in a day you would get it. There was a question, yes? Yes. So I use here head in front of all my function because I just want to keep everything on the same slide. Otherwise, I mean, it doesn't fit. Here, the head is to display the first 6 rows by default. But if you put, I mean, a second value after the second argument, you display as only the number of rows you want. And in my case, I mean, to fit everything on the slide, I just say display the first 2 rows. You suppress head and the brackets around it, and you will obtain the entire value inside your R session. So you will output everything. Okay, that can be, in fact, too much to display on a screen. So what you would like to do is store that into another object using the assignment thing that we saw at the beginning. For example, you would say you would type you want to store all the people which are male into your data frame, and you want to store that into a new table. You would say the table is called, for example, X, and you put equal to SQL, and you type your query after that. Another small gem that I really like is do-by. It's a package which is providing, I mean, even more complex function. So you can make a summary of your data directly within one command. So you say summarize. That's a classic data set which is called iris, containing the dimension of the petal of the flowers, of the width of the sepal, and everything, and species of flowers, of iris flowers. And in my case, I want to have the summary by where I make the summary of the sepal width by the petal width, and organize that by species. And the function that I want to apply is the mean when you have duplicated value and duplicated rows. And what you obtain is a table with species as rows. That's what we specify here, by species. And you have the sepal width mean and the petal width mean in the column. It's pretty powerful. It's a summary function. But it's an advanced example that I just put here for your own knowledge in the future. Connecting to database. So before we switch how to export file, I will show you how to connect to database. Most of the time, your file, at least in my work, they are not in fact text file. We store our data inside database because they are too big. I mean, it's way too big. We cannot have text file all over the place. So we store our data in database. As an example, I work on, in my lab, we work with patient data. So we extract data from the hospital. We obtain data from the IRT team. After IRB approval, we have our extract. The extract are patient data. We import that into our local database. And what I do is that I basically run all my analysis within R, and I query the database from R. So I don't go onto the database by myself. It's R. I write SQL query within R to extract the data. Here's an example. So the database is, I connect to a MySQL server. So MySQL is a relational database. You have other databases like Oracle and PostgreSQL. But basically, you have drivers for them. In this case, I use a package called RMySQL, load it, and I say connect to the database, MySQL. The user, you have to type your user, your password. You type the database name, because you can have multiple databases on the database server. In our case, that will be the patient data. And we say where the server is. You give the address at Stanford. And after that, you do a query on your database using SQL again. And SQL is fairly easy. For example, here we have a table which is called patient table, so PAT table, all right? And we want to select all the elements inside the patient table, but we want to only the 5 first rows of the table. And that's done using the dbGetQuery function. You say you want to connect to this database, the con, so that's defined here. And you say that the query you want to accept to perform on your database. Pretty powerful because you don't need to do that on a separate software to run your SQL query and obtain a table that you would save to a text file and then import into R. you do everything within R, and what you obtain inside the object result here is in fact a data frame. And here you see that the result, and you have the ICD-9, you have the disease, and you have the count of patient and count of encounters for the patients, for those different diseases. So it's an integrative environment. So you don't need to go outside of R to run, another language. So you type another language, SQL, within R. And that's pretty powerful. So exporting data. So the thing is, once you have everything inside R, your flow cytometry, proteomic data, mass spectrometry, macros, ChIP-seq, SNPs, whatever you want, you do your analysis, you produce your graphics, statistical analysis, you transform your data, you annotate your data, and you want to export it. So how to save it is that first you can save your environment. So all your work, everything you have inside R, you can save it. And you can save it using the save function. And you say, what are the objects you want to save, for example. In this case, you want to save the pivot object, which is a table we use, and the matrix, mat, which was a simple matrix. And we say we want to save that into a file called data export, and you put an extension. The classic extension for R is .rda for R data, but you can put whatever you want. It's as long as you know what it is, it doesn't matter. It will matter for your operating system to recognize the file, but it's not the thing. And after that, when you export your data into this R data object, you can re-import it in any session of R using the load function. And you give the name of the file, data export.rda, and you re-import the pivot and the matrix object into your new R session. Okay? So it's a way to export R object into another R session. It's not to export to somebody else which don't use R. Okay? For that, you can write your object to text file if it's suitable. So if the result of your analysis is a table, a matrix with, for example, p-values with the differentially expressed gene or differentially expressed protein or whatever you have, you can do that with the write table function. So you say write the table, and you write your object, which is a matrix. You give the name of your object, and you give the file name, and it will be matrix.csv. That's the name of the file I choose. And you see, you give the separator between the field of your table. And here, in my case, I gave a comma for comma-separated value. If you type /t, it will do a tabulated format. Fairly easy. You have a lot of functions to export to other software, if that's the thing you want to do. For example, you want to export your matrix to a SAS object. You can export that, and you can write to SAS and write export. And you load a library called SAS export to SAS. If you want to write to R file, which is a Weka file, which is pretty tricky to do, is that you use write auth or write DTA. I think DTA is for SPSS, which is data mining software from IBM. It's all stored inside the foreign library package function. Is it clear? So that will be, before we switch to an example of importing gene expression macros. Is there any question at this stage? We are about an hour inside the tutorial. Yes? Sorry? The R MySQL, you need to install the MySQL database thing before. Otherwise, it will tell you, well. Yeah, I can see that after for installation problems. Yeah. Question on the language, yeah. You use that, let me show you. So for example, we have the mat object, which is a matrix, okay? You want to write, you write the table, okay? And you say you want to write mat. And you say file, and you say, for example, you want to write that on the desktop of your laptop. And here I'm not in the desktop, so I will put the path to the desktop. In this case, that will be users, DRUO, desktop, and you say the name, and that will be mat.txt. okay, between quotes. That will do it. Type it, and it wrote the matrix. And you can go to your file, you can open a new one, and you have mat somewhere. Here you go. And mat is written like that, okay? Yeah, but that will work maybe on a Mac, but that will not work on a Windows. So that's why I try to keep that. I mean, so the paths on a Windows, are, I mean, tricky detail is that the path is written with inverse, okay? So it's a different thing. Let's go back to the tutorial. All right. So right now we'll see an example how to import data from Gene Expression Omnibus, which is an online database where a lot of macroarray experiments are available for free in a way. They are publicly available. There is two main repositories that we'll use today. The first one is Gene Expression Omnibus, which is the American repository, and you have ArrayExpress, which is the European counterpart of it, which is stored as this database, in fact, stored at the EBI, the European Bioinformatics Institute in Cambridge. Both are giving access to the same data, so they are kind of mirror of each other. Today we'll download one package, one data set from the online repository, and that's from this paper. It's a paper where I was a co-author on it a long time ago. That's why I chose it. So we analyze pluripotent stem cells. So we did a small experiment where we have 3 types of cells we derive from the same original somatic stem cell. We apply an operation. We just use OCT4 and we reprogram the somatic cell into induced pluripotent stem cell, and we try from the pluripotent stem cell to regenerate the somatic cell. So it's kind of a loop, and we were comparing, in fact, the expression value between all of them. You can download those data. I uploaded those data after we published the paper. I mean, upon publication of the paper, you have to submit those data online. You go to the GEO website, you submit your data, and you give the raw data to Gene Expression Omnibus. And that's what I did. And now, because I did that, everybody in the community and who want to reanalyze those data can download those data and reanalyze that directly within R. So you don't need to do that somewhere else. I use a bunch of libraries that I don't ask you to install right now because it will be complicated, but that's the library which are required. Library Affy for Affymetrix data, because that's the type of macroarray we use. GeoQuery to query the online repository, Gene Expression Omnibus. And we use also the annotation package. We perform that on mouse cells. So we use a mouse Affymetrix array. So we need to have an annotation package, which is a mouse 44302 CDF. Basically, once you know the GSC, which is the Geo Seri ID of your experiment, which is online on Gene Expression Omnibus, so you go to the website of Gene Expression Omnibus, and you search for your data set. Every time you will search, you will obtain, a bunch of data sets which are on a web page, like a search result. And you will have a code, a GSC number, 1234, whatever it is. You just type get geo supplementary file, the code between quotes, and everything will be downloaded to your laptop. And that's it's quite powerful. So if the person that submitted the data submitted the raw file, the cell file for Affymetrix, you will be able to download that. Of course, if the raw data are not available online, because it's not required to put the raw data, it's required to put processed data at the minimal data you have to submit. But if the person submitted the raw data as cell file, you can download that. So it worked for this example. It might not work for every data set. It's something which you need to know in advance. After that, that's what I meant by system specific. So you need those files are compressed. So they are a zip file. So you need to uncompress that. I do that within R here using the system function. but you can do that on Windows or on your Mac, and you basically double-click those files and you expand them. You open those files. That's not really important, this step. And after that, once you have your cell file inside on your laptop, basically what you do is that you use the function read_afi. You give the cell file path, and you give the path to it. So it's inside a folder called GSC12499, which is in fact the name of the ID of your experiment you just downloaded. And boom, you have your raw data inside R, and you have gene expression data. In this case, when you describe it, it's a bit short on this thing, but at the bottom here, you see you have 10 total, meaning you have 10 microarray data. So microarrays, in fact, which are uploaded inside your R session, inside the DA object for data. So, and basically you can start doing data analysis on this object, on this microarray data. You can normalize it, you can do whatever you want with it. You can extract what are the differentially regulated gene. We'll see that tomorrow, in fact, on the same data. Or to extract in 5 commands, you can extract the differentially regulated gene between 2 conditions. All right. So the same thing can be done on ArrayExpress. ArrayExpress, so you have a package called ArrayExpress, and the package allows you, in fact, to do even more complicated thing. So you can query the database directly from R. For example, in this first query at the top, I'm looking at query AE, so ArrayExpress, with the keyword pneumonia. And the species, I say it's a Homo sapiens species. So I just want the data set which are in ArrayExpress, which are annotated with pneumonia. And it will give you a list of data sets. I mean, quite a huge list. So you can do that automatically within R. You can do that online. You can go to the ArrayExpress website and also type pneumonia and humans. And you can obtain the same result. But basically, yeah, I just output what are the first 3 data. And it returned to you that the ID at the beginning, GOD24, and you have the ID, the row, do you have the raw data available? Yes or no, that's the first column. So that will tell you, in fact, if in fact you can download the raw data from this experiment. So if you don't have the raw data, most of the time you will be stuck at this point because you cannot assume, and you don't know what was the normalization procedures they used. So merging data with other data set would be a bit tricky. Is it processed? Yes, usually you always have processed data. And here is an example for a data set. In this case, we just type, instead of in gene expression omnibus, we were having the same thing. We were saying get geo. Here we say get AE for ArrayExpress. We give the ID of the experiment, and we download the data, and we want the type processed. So we want the processed data already normalized. Everything is done. And you have a bit of mumbo jumbo about how to replace and the annotation. So that's a bit like you have to do that. You build your expression set. So from the raw data that ArrayExpress gives you, you have to build an object which is called an expression set. That's the start of everything. So that's a requisite, and you have to type. You have to process and generate an expression set before you're able to analyze further your data. The expression set is already done. So if you look at this command line here for Affymetrix for gene expression omnibus, read_afi is doing everything for you. So you don't have to, in fact, build an expression set for you. It's just that the package ArrayExpress is a bit working differently, so you have to work on it a bit and to generate your data in the right format. In this case, this object with the ID.da contain 18 samples, and you have 18 microarray samples on your laptop ready to be analyzed. Just wanted to mention, so a nice way to learn R is maybe to have a look online, and you have a link to inside Gene Expression Omnibus, inside Geo. On the web page, when you look on a data set, you explore what the data set was about. For example, it contain the cells that were treated with a particular drug, you have at the bottom, you have gene expression omnibus to R. You have a button for that. So let's have a look. It gives you a web page where you can, in fact, search for a particular accession number to GEO. And in this one, you type, for example, an accession number that we used before, GSC 2050. It will give you this table, and you can see you can annotate your data directly. So you see at the top, I said the group will be the blue group, and I define that will be the control. Yeah, in the first column, and the one at the bottom will be the disease. Okay. You annotate your data online. You have the web interface. It's really easy. You will understand. It tells you that in fact you can annotate your data with groups. Going further is that you say run at the end and give me the top 250 genes from your data, and you have the result inside GEO2R, which is a tab. But if you click on the tab called R script, you also see the R code that was run in the background on gene expression omnibus servers for you to generate this 250 differentially regulated genes list. So it's a nice way to learn R in a way, and to see how do you, in fact, query data. So you can take this code and run it on your laptop directly. It run it for you on the NCBI server, but you can also run it on your laptop using R. So it's a pretty powerful feature to learn how to analyze macroarray. You see that it uses getGeo, the same thing as we did. And after that, if you scroll down, you will see how it normalizes the data, extracts the data, and or extracts the top differentially regulated genes. It's nice if you want to analyze only one data set. If you want to analyze a data set which is more complex, or to combine different data sets, you cannot do that within this interface. So, yeah. Here I have a few slides on, in fact, I think one slide on working with big data. So what happens if the data set you have is huge, immensely huge, and you have like a table which is, giga and maybe, 100 giga of size. You cannot work with this data directly within R. You cannot say read the table and put that in R. R will fail because you don't have enough memory on your system. So what you have to do is you have to find another way to store this data and work with it. The first thing that comes in mind is that if you can, build a database. Okay, so the database can handle really large file, and in fact you will be able to query this database and access those data more precisely within the database, and it will be faster. The second, for example, take a look at MySQL or SQLite, and that will be a nice start. If you want absolutely to work within R, you have some package which allow you to work with huge data, and they are called FF or Big Memory. There are two packages. They provide different functionality. You have to choose one. Big Memory is a bit easier to use. Big Memory is giving, nice interface. It's a bit the same, but you have to choose one anyway. So the difference is that using this type of package, you will use a new paradigm to interact with your data. You will not have really a data frame. You don't have a list, a matrix, or a vector, or a data frame. You have a big memory object, which is a new type of data, and it's a file which is a binary file stored inside on your local hard drive, and that will allow you to query those files really quickly. Faster than if it was within R using a regular data frame. But sometime, you reach the limit of R. R is a statistical language. It's meant to mean N-level analysis, such as a statistical test. And in this case, you might want to take a look at other language to help you. And for example, there is a Python scientific library, SciPy, which is providing really nice tool for working with big data. But it's a different realm. It's a new language. You have to learn how to code in Python or in Ruby. And in particular, for example, in Ruby, take a look at the GSL and GNU plot gems. It's powerful. So not everything is is anchored into R. You know, R is a platform to analyze, to perform some of the operation, but it's not perfect for everything. So you might want to, learn about database or big memory or other language. And now we'll switch gear. And before we after this introduction to R, long introduction to R, and quite fuzzy, I should admit, we will have an introduction to the basic of programming inside R. And that will be in the last step before we finish the class. We have I hope to have 10 minutes of time at the end to answer questions and for your assignment. So programming in R is a bit like programming in any other language. You have the 4 type of functions. So you have if conditions to test something. You have for loops to repeat an operation until it ends or until a condition is reached. You have while loops, and you have assignments, such as storing data into variables. We already saw this. So let's start from the top. The if-else condition. Okay. So here I do an assignment. I store inside the variable I the value 1. Okay. You can also do it with another sign, which is equal, okay? You can say I equal 1. It's the same. It's a bit redundant. It's you don't know really why they provide those 2 functionality, but it's just stick to 1, and I usually stick to the inverted arrow to say store inside I 1. So the assignment sign instead of equal. You can choose equal if you want. And here is how you use if. So you say if I, and here you want to have a test. You don't want to have an assignment, so you use double equal. Okay? If I is equal to 1, output this thing between the curly bracket, print I is equal to 1. Okay, and it will output the text, the thing. If it's not, else, okay, if I is not equal to 1, print I is not equal, so print something. When you run it, and you run if, and you see, it will tell you I is equal to 1, all right? And that's the answer from the function. Pretty basic. So that's programming 101 in R. It's highly similar to other language. If you are familiar with any other language, it's basically it. That's it. Here you have a shortcut, which is always provided. So R, you have multiple ways to do the same thing. If else is a function that will allow you to test in one command line. So on the same line, you don't need to write curly brackets and everything. You just say if else I equal 1. The first argument between the comma, okay, is yes, and that's no. Okay. So if I equal 1, output that. If it's not, output that. So that's the if else command. If you want to know more, use question mark if else, and you will have the help about this function. And the help will tell you what does it do, what are the options in it, and everything. Is it clear before we switch to a bit more complex things? All right, I never know. This thing is, this programming language level is, I don't know if everybody is familiar or not, but I have to cover it. It's prerequisite to have everybody at the same speed. So the second structure, major structure, is for loops. So for loops is if you want to repeat an operation over and over until you reach a condition which is fulfilled. Here is a pseudo code. So it's not R code. It's a code to explain you how it works. Okay. So for I equal to 1 to 5, do this operation within the block, and end when you end the for loop when this condition is reached. So when I will be equal to 5, it will stop. Okay. So in this case, that's the R code on the right, okay? For I in 1 to 5, so 1 to 5 is a vector, 1, 2, 3, 4, 5, I will take the value of, which inside this vector, 1, 2, 3, 4, 5, sequentially. So I, in the first loop, will take the value of 1, in the second loop, value of 2, third loop, value of 3, 4, and 5, and it reached the end of the vector, and it stopped, okay? So you will execute 5 times this loop. And each time you execute this loop, you will execute what's inside, and you will have print I, which will print you the value of I, okay? And you will see, in fact, the output here, and it's 1, 2, 3, 4, 5, which is basically it. So you can imagine you can combine a for loop with an if-else inside. So you want to execute an operation on a vector, imagining. And you want to execute the value on the vector if you have a condition which is fulfilled. So, and that's what we'll see in the next, at the end, to combine and try to program a bit more deeply. But always, I mean, as I mentioned, in R, you always have a way to do the same thing differently. So the apply family of function allow you to apply a function to a vector or a matrix in a really convenient way. We take again the same example. We have a matrix of 10 numbers on 2 rows, 1, 2, 3, 4, 5, 2 rows, 5 columns. And we want to apply this, we want to sum the matrix, okay? But we want to apply and extract the sum of the column, okay? So we want to make the sum of 1, 6, 2, 7, 3, 8, 4, 9, and 5, 10, okay? So by column. How to do that is that you say apply to the matrix, and you say the index, so 1 or 2 here, 2 will be the column, 1 will be the row, and you say apply this function, sum, and it will output you the vector, 7, 9, and 2, 15. So if you want to sum on the row, as I mentioned, you can also use the first index, and you say apply to the row, okay, 1, and you say sum over the rows, and it will output you the 2 numbers, 15, 40. So it's a way to apply a function over a matrix, and you can even apply that to a function over a vector, and you can build your own function on it. Of course, another way to do it is to use the already made function to do the row sum, and you use row sum on max, and it will give you directly the output. So row sum at the bottom. It's inside the output. So you don't have the last line of my screen. It's not showing here. Is it clear for everybody? So the apply function is a kind of a nice function within R. You have, I mean, like a lot of little function to simplify your life like that in R, and it's pretty nice. Let's go a bit further, and let's look at doing efficient R programming and using multiple core to program inside R. So as I mentioned, most of you have recent laptops, and there is certainly, in fact, a dual core or a quad core processor inside your laptop, meaning you have, in fact, 2 or 4 processors inside your laptop. This thing is that this power is not usually, used efficiently by your laptop. You usually use only one of them at a time. But if you want, to compute faster, you can use the 4 or the 2 core of your laptop. On my laptop, which is, more than 3 years old now, I have 2 cores on it. And to program and to say, well, you can execute things in parallel. You run that on this core and on this other processor. So you have 2 processors in it. So to do that, you can use a library which is called for each. And you have to load a bunch of libraries. So for each, do multi-core and multi-core. So next line, so that's the library requirement. You have to load that, you have to install that. It's, once you are there, when you install it, you can start programming using for each. Okay? Here is the thing. We use this function called multi-core and column, 3-column detect core. And it will tell you how many cores there are on your laptop. So you don't need to know how many there are. There is a good chance that all of you have 2 core only, okay? But if you are not sure, if you don't know, well, you can use this function, multi-core, column, detect core. It will store inside n core. N core contains, in fact, the value of the number of core you have. In my case, that will be 2, the integer. We register the number of core we use. We want to use the 2 core, all of them, which are available on your machine, okay? And we execute a for each loop. So it's a for loop, but made to use multi-core processor. So it will dispatch the work on every processor on your laptop. It's not only focusing on one core, it will dispatch the thing as much as it can, okay? So in this case, we do the same thing. We will add 1, and we'll add the 2 value of I. So it's a for loop. The first time you will run through it, I, which is defined here, will take the value of 1. Second time it runs through it, 2, 3, 4, 5, and it stops. Okay? The same example as we saw before. And in the middle, we do an operation. What we do is that we do the value of I plus value of I. Okay? So the first time you run, it will be 1 plus 1, 2 plus 2, 3 plus 3, etc. But the key is that you will not run that on one processor only, you will run that on all the processors available in your machine, just using for each and this command in the middle, do par, okay? And the results are still in, so meaning the 1 plus 1 operation, so the first time it will run through the loop, will be dispatched to one core, and the 2 plus 2, so the second time it runs through the loop, is at the same time running on the second processor, okay? Not waiting that the first one is finished. And you can have, in fact, a faster processing like that. But the key thing is that don't be afraid that your result will be messed up, because if one core finishes before the other one, the result will be returned and not in the same order, and according to which core was faster. So the thing is that the result will be kept in order. So it's that's the beauty of it. So here, in our case, we keep the result in order, 2, 4, 6, 8, 10. Is it clear? So in the space of 6 lines, basically we did a multi-core processing operation. You can imagine that you run that on a bigger machine. Okay, you have a cluster or you have a huge machine in your lab, which has maybe 16 core on the machine. It's not rare. It's basically 2 processors with 8 core each. That's the last Intel processor chip. And you can run an operation 16 times in parallel, instead of running that on one processor at a time. It will speed up your code by approximately 14 to 10 times. So every operation you imagine take long can be divided by 10, at least. So it's a pretty powerful way to code, I mean, and I encourage you to use it. There is some detail about the thing is that there is an overhead, because you need to pre-process the data to know how many functions you have to dispatch. There is often, in fact, a cost to use multi-core. So it's efficient if you have huge operation, but it's not so efficient if the operation is really simple. And that's an example. You remember the apply function. So it's a way to apply the same function again and again really easily in R over a matrix, for example. We saw the example with the sum. The MCLApply is an apply function for multi-core. So it will dispatch the function you give to your matrix across all the core available on your laptop or on your machine. So, but here we will do 2 things. So we load the library at the beginning, library multi-core, R benchmark, to compare the speed between the implementation. And we say MCLApply, so the multi-core function, and we apply R norm, and we compute, in fact, a normal distribution inside R, and we compute that n time. All right? And we use the classic function lapply, which is not multi-core, which run on one processor at a time, and the other one run on multiple processors. Okay? And we say we want to repeat this test 20 times, and we want to average and take what is the average runtime for those 2 processing steps. And we want to see which one comes first, which one is faster. And that's the result. So you say 10 replication, and you see the unlapsed time. So the test number 2 comes first, and as an unlapsed, if you see, it's, okay, you just have the first line on the screen, but let me show that. Okay, you have here the first line, which is it took, in fact, per run 0.028 seconds to run. That was a regular one-core processing function. Okay, and here we have the multi-core processing function, which should be faster because it dispatches the work to all the core possible. Okay, but it took longer. It took 0.5, half a second to run. And in this case, we are not really, so you have a factor of 8 19, almost 20% increase in time using multicore. It means the multicore function is not so efficient for doing small tasks like that. And because there is, it will become faster as soon as you have more and more replication and more complex function. A small what? Oh, the limit is, you have to make some tests. You don't really know. It depends on the number of core, it depends on the library you use in the background. Usually I use multicore when, for example, I have to do linear regression, or you have to do a t-test, okay? So if you have to repeat a t-test multiple times for each row of your data, well, you can use a multicore thing. It's faster in this case. Some functions are not faster. Some are way faster. So, and that will be the last step, and before we see about writing function and a bit of object-oriented programming, we'll write a function, a simple function. We want to compute the Euclidean distance. The Euclidean distance is a distance, basically in a 2D plane, is a distance between 2 points. If you take your ruler, you can do it. That's the Euclidean distance. How to compute the Euclidean distance is, you all remember your first class in primary school where you have, to compute what is the length of the hypotenuse of a rectangle triangle. You know? So it's always the same thing. That's the Euclidean distance, okay? You can generalize the Euclidean distance to more than 2D, not only the 2D space of your paper page, but to multiple dimension, 3D and 4D and whatever you can imagine, if you can. And here is how to write a function in R. So we write a function that we'll call Mr. Euclid, and we say we assign to Mr. Euclid, which is an empty object at the moment, a function, okay? And we say it will be a function with two arguments, x and y, which will be in fact the 2 points in space, and you want to measure the distance between them, okay? And you want to, that's the formula to compute the distance between 2 points in space, is that the difference, the square difference of the sum, and that the square root sum difference of the square. Okay? Or something like that. Yes, that's it, yeah. Square root is the sum of the square root difference. Yeah. And you return this value, okay? So the distance. So imagine you have a point which is defined in a 2D plane, and its coordinates are 1 and 1. So 1 on x, 1 on y. And the second point is at the level 2, so it's 2 and 2. So it's a 2D. You have 2 points in space. That's what we define it. So we define x as being c equal 1, 1. So we say it's a vector, okay? And it has a coordinate 1 and 1 in space. Y as a coordinate 2 and 2. And we want to compute the distance between x and y. That's what we do here. We say Mr. Euclides, and within round brackets, we put the two vectors that we just built, x and y, and it outputs the value of the Euclidean distance. Okay? Is it clear? So that's the basic how to build your own function in R. It's fairly easy. You don't have to do, really complex programming and anything. It's you just write it's a function. You say what type of argument it will accept, and you say the operation it should do at the end inside, and you say return, and return what? Your object with your result. All right? So, sorry? You save it. It's saved. When you type, in fact, the assignment here, Mr. Euclides arrow, it will save it as a Mr. Euclides function. Yeah, yeah. You still call it, yeah. I recommend to save your code all the time, in a text file on the side. You don't do everything on the command line. You do everything in a text file, and you copy and paste into your. You have a programming, timeline in a way. So, for example, I have it here. You have the function; it's inside, and if I don't give any square round brackets after it, it just outputs what's inside the object. And here it's a function is x. So it contains not the same code here, because we'll see it's in fact the last version. We'll just see it right now. But what is the problem with the function we just wrote? Could someone tell me what is the major problem with it? Is that if you give something else you don't give the right data to Mr. Euclides, what will happen? Bad thing will happen, yeah. Bad thing will happen. So basically, if you give a vector of characters, a plus b, a, b, and y is 2, 2, the function will fail. And it will output a cryptic error message saying, well, I cannot compute the square root difference between a character and a numeric value. So, and at this point, if you want to provide your function and don't want to use it only for you, and you want to provide your function to other people, you might want to program that more carefully to avoid that people give as argument to your function some really weird vectors of anything they want, okay? And contact you every time by mail, every time it fails. So a classic thing is that you would use a new paradigm, so object-oriented programming, and you would say you have to give, in fact, to the function a vector, and you would check for it. So you would check that, in fact, the object is of the type you want, okay? So the object is, for example, in our case, it has to be a vector of integers. So it's not really robust, as I mentioned, and x and y, in our case, in the actual state of the function, is that x and y have to be numeric vectors. And we don't even wrote, in fact, a documentation for our function at the moment. So. And this is implicit. No check are made, and you try to compute the clean descent with something else, it would fail. Okay? To overcome such deficiency, you can use object-oriented programming. In R, they are called S3 and S4 system. And if you start using R right now, you will just learn about S4. S3 is an old system. It tends to be deprecated. And that's how you build an object. An object that will be of the type you want, okay? So imagine you want to build a really robust Mr. Euclides function. The x and y will not be vector anymore. They will be, you will check if they are of a specific type of object, not a vector, not a matrix. You will call that my object, okay? And you will say, what is it, my object? So you have to define what is inside my object. And you will say, the representation is a numeric vector, okay? It has to be numeric. And the default argument will be, the name inside my object will be vec, okay? And the prototype is, so the default value for vec is here, okay? VEC, that will be the name of your argument inside my object, will be 0 by default. So here, for example, I initialize the my object function. Not function, but my object object. Not a good name. So you define my object, and you say, within my object, I want to store the vector of 1, 1, 1. Okay? So it's a coordinate in 3D, okay, of your data point. And vector A will be the value containing, in fact, your vector. And you see, when you output vector A, it will give you that, an object of class myObject. And the slot for vec is containing a vector of integers, okay? And it has to be numeric because we define it as numeric. So you cannot store inside a myObject object, you cannot store characters. It would tell you it's not the right type of data. And that's how you would enforce the type of data given to your function. So let's see. You have to modify, now you have to build a checkup system inside your myEuclides function. MyEuclides, you wrote again myEuclides, you store inside myEuclides a function, x and y, and you say, you make a check on the two arguments that were given to the function, x and y. So you say, if the class, so the class will be the class of the object, x is not my object, and the class of y is not my object, you make stop and you say error. You can write something a bit better than error, okay? Because that will be the output of of the function, if you don't give a myObject object to Mr. Euclides, it will output error. If you write something else here, like you should give an object of the type myObject to Mr. Euclides, here's how to do it, and you can write a long thing, or check online for detail of how to use Mr. Euclides, and that will be the output of your function. And here you do the same thing. You compute the distance between the two objects, but you have to access it. So you say x, and you access a vector inside x, and you access the vector inside y, and you compute it, and you return the distance. Here's a test. So we build another vector called vector b. We have vector a, vector b. We say it's a new myObject function, myObject object, and we store the coordinates, so 2, 2, 2. That was this, another coordinate for another point in space. And we compute Mr. Euclides with vector a, vector b, and it gives you the distance. Okay? The root square of 3, basically. Here I give you already, so we wrote a function, Mr. Euclides, which is not really needed per se, because it already exists. So you can already compute the Euclidean distance within R, so there is already a function to do it. And as a sanity check, we can in fact compute the Euclidean distance using the library biodistance, so biodist, and you use Euc, which is Euclidean, the function. They don't call it Mr. Euclides, they call it EUC. You give the value to it, and it will output the same value to you. So it's a sanity check. We obtain 1.73, and here you also obtain 1.73, meaning we computed the Euclidean distance correctly. If you want to learn more about how to program in R, and especially about the detail of object programming and how to build functions, detailed function, complex object with inheritance and different class, you can have a look at the book R Programming for Bioinformatics. That's been written by Robert Gentleman, so it's on your printout. Robert Gentleman also wrote the R language, so you know what he's talking about, and it's a really nicely written book. Contrary to many programming books, it's not so rebarbative, so you can still look into it and learn some things from it. So you have a lot of little code inside the book that you can copy and paste and try for yourself and see what failed, why you failed, and everything. Okay, it's a nice way to learn. And we are reaching 20 minutes, so we'll have the assignment for tomorrow is. If you want to do it, you're not obliged to do it, but it will be fun to see what you come up with. Is that I would like you to write a function to generate the first 50 numbers of the Fibonacci sequence. So the Fibonacci sequence starts at 1, and it starts like this. So 1, 1, 2, 3, 5, 8, 13, 21. It's basically the two first numbers are fixed. Okay, it's 1, 1. It's a couple of rabbits which are reproducing, and so they mate and they obtain 2 rabbits. Okay, and so it's how to build the next number in the Fibonacci sequence is to sum up the 2 preceding numbers. So you have 1, 1, and the third number would be 1 plus 1, and the fourth number would be 1 plus 2. The 5 would be 2 plus 3. 8 would be 3 plus 5, etc. Okay. So you can compute the Fibonacci sequence like that. So the Fibonacci sequence number for your level. So you are, for example, you want to compute the Fibonacci sequence for level 50. So what is the Fibonacci number at level 50? Will be the sum of 49 and 48. Okay, the level 48 and 49. Okay. So of course you need to have the Fibonacci number need to be computed for I superior to 2. If you don't have the 2 preceding numbers, I mean you don't have them to compute the sum, so you cannot compute them. So the bonus would be that you write first a for loop to build this Fibonacci sequence. The bonus would be, in fact, to build it as a function. So to store your for loop inside a function to see what argument you would need to build a function with a Fibonacci sequence computation inside. And tell me if you can try to implement a parallel version using the for each okay? And why you failed. And would be a nice way to experiment with for each. Okay, or if you manage to do it, that would be good. Okay, so that would be the assignment for tomorrow. If you have any question, I mean, right now that could help everybody, I think. So it's a quite heavy technical lecture. You saw a lot today. I acknowledge that. It's you will need a bit of time to digest it, and that's why I provided the handout, and also you have the online website where you can copy and paste and try the code for yourself. Okay, and tomorrow will be a bit more high level. What can you do with R? You can also, there will be also some code if you want to try it, but it will be a bit more like high level. You can do that. The code is online. I will not ask you to do it right now in the class, and that would be it. So if you have any question on any aspect like import, export, or to write functions, object-oriented programming, and basic thing. So installing package can be tricky, okay? So it depends on your machine, depend if the package is provided, and work on your type of operating system, Windows, Mac, Linux. It's that could be tricky, and that's the kind of question, I mean, I'm happy to answer them, but it's not really pertinent to everybody, I would say. Any question? Yes. Yes, between quotes. Sorry. Yes. So yeah. So the question is, in the last implementation of the Mr. Euclides function, why do I use the arrow-based sign and not a $sign? It's because to access an object, so inside X is a myObject object, okay? And you can have multiple slots inside. We have only one slot, which is called vec, okay? And vec can be accessed within X using the arrow base. It cannot be accessed using the $sign. The $sign, I mean, it's linked to the fact that it's the representation. It's S4 object type, and S4 object type are accessed with the arrow base sign. There is not really any reason for it. You have X arrow base at, X at vec, and we'll give you the value of vec. No, my object is a name. The name of the class. In fact, it's the name of the class, okay? So you could call it David, you can call it whatever you want. It's the type of object you have, okay? So you can have multiple objects called my object or David, you know? And you can call them like as you want, okay? Usually you have to find a name which is meaningful. And so here, for example, we call them my object at the class, and you want to check if the object is of the right class, okay? So it allows you to have kind of a meta annotation on the type of object, and not have an object you want to check if it's a class X, Y, Z. All right. So that's the thing. Is it answering the question? Does it make sense? All right. All right. Any other question? No. So tomorrow's a lecture. So there is a sign-in sheet in circulating. If you haven't, it's here. If you haven't seen it, please sign your name. We don't. All right. Please sign your name on this, and that's really helpful. Otherwise, we see each other. If you don't have any question, regarding everybody, you can come and ask me a question right now. And otherwise, we see each other tomorrow at 10 a.m. for the second part of the lecture on R programming. Thank you.